In section 6.1, and we have introduced a integration method to determine the deflection of loaded beams. I believe you have all experienced the difficulty in this method. Why this integration method is very complicated. I can tell you that the integration method is perhaps the most difficult part of mechanics and materials. You have to do integration. You have to determine the constant values based on boundary conditions, and then solve them step by step and derive a expression of the deflection function, right? But here comes the good news. Section 6.2, we will introduce a much simpler method, which is called superposition method. It means that we have derived all of the equations for simple beams, for simple loadings. So for any complicated case, you can just split the complicated loading distribution into combinations of simple loadings. Then you can solve them one by one and add the effect together. You can get the overall deflection of the beams. Okay, so first of all, let's look at two big tables. In the first table, you can see simply supported beams with different loading, simple loading. And for each one of them, you can see the equations for slope, equations for deflection, maximum deflection, and equations of the elastic curve, that is, expressions of the deflection function of deflection. So let's look at the first one. In this first case here, okay, when you have a simply supported beam, which is loaded with a concentrated load P at the middle span, and you can use the equation 1 to determine the slope at the left support and the right support. Of course, at the left support, the slope is a negative angle, and on the right hand side, the support 2, the slope is a positive angle. And the maximum deflection appears at the middle span here, right? So you have the maximum deflection, and the overall elastic curve is expressed by the equation number 3. But I have to remind you that this equation is only applied to half of the beam, from 0 to half L. That is to say, if you want to know the deflection at a random point in this range, from x equals 0 to x equals half L, you can use this equation. Just substitute the x, use a specific coordinates, x coordinates. Then how about if we want to know a deflection in this range, where x equals half L to L? Obviously, you cannot directly use this equation, number 3, because it's only applied to 0 to half L, right? So then what can we do? If we want to know the deflection at here, right, at 3/4 L, what can we do? Okay, in this case, you should know how to use this equation, right? If you want to determine the deflection at this point, you should reconsider the system. Consider the x starting from the right end to the left hand side. So here is the x. Okay, if you consider the x start from the right hand side and point to the left hand side, then you can use the equation 3 and substitute the x using, of course, using 1/4 L. X equals L over 4. right? So substitute x using 1/2/4, you will get the deflection at this point. Right, then in the second example, okay, in the second one, so when you have a simply supported beam while concentrated load P is added to a random point here with the distance to the left-hand side A and B to the right-hand side. So in the same way, you can see the equation 4. Using equation 4, you can determine the slope at this support and the slope at this support. Again, on the left-hand side, you have a negative slope, and on the right-hand side, you have positive slope. Right? And using the equation number 5, you can determine the maximum deflection that is here at x equals a. And the equation number 6 is the elastic curve, which you can use to determine the deflection of a random point within this range from 0 to x equals a. Again, this equation is only applied to this range. Then how about if you want to determine deflection at a random point in this range from a to a plus b? Right, this obviously you cannot use this equation and substitute x using a plus a random x bar. Right, you cannot use this equation directly. So in the similar way, if you want to determine the deflection in a random point in this range, you need to reconsider the x, set the origin of x at the right-hand side, and the x point to the left-hand side. So in this way, you can use this equation. Of course, you need to change b to a and a to b. Right? This is how to use these equations flexibly. And other equations are simpler. They look more complicated, but they are actually simpler because they do not have the application range problems. And in the second table, you have cantilever beams, and you have many equations. Okay, let's look at the first one. You have a cantilever beam with a concentrated load at the free end here. Right, if you want to know the maximum slope, obviously the maximum slope will be here, right at the free end. Right, you can use this equation to calculate the value. And so what is the slope? What do you think is the slope here at the fixed end? What is slope? Right, it should be 0. Okay, then the maximum deflection also appears at the free end, and its value is here. So if you want to know the elastic curve, that is the expression of the deflection distribution, you can apply this equation. If you want to know a deflection of a random point, let's see here, x equals a, then you can just substitute x by a into this equation. Then you can get the results. Well, that is the deflection at this point, x equals a. Okay, just use these two tables. The superposition methods can be expressed in this way. It has 3 steps. In the first step, just split loading into simpler parts. For example, here we have a cantilever carrying 2 loads. One is distributed load W, and another is concentrated load P. Right. So if you want to split it into simpler parts, well, it equals these 2 simple cases. In the case number 1, this cantilever only carries distributed load W. and it will have deflection distributions as shown by this curve. And the case number 2, this cantilever only carries concentrated load P at the right end, at the free end. You will have the deflection distribution curve as shown by this orange curve. So here you will get a delta 1 and delta 2, two components at the free end. And if you want to determine the total overall deflection at the free end, just simply add them two. Add the delta 1 plus delta 2, you get the delta of the free end under these two combined loads. Okay, so this is the superposition procedure. Okay, just let's leverage this example and look. That is our example 1. Okay, determine the beam deflection of beam at the right end. Okay, so we have exactly the same example here. You have a cantilever carrying distributed load W, concentrated load P at the free end. Then we're determining the deflection at this end, delta. Okay, this is described here. So as we just shown in the previous slides, what we need to do is to split these two loads, split the combined load into two simple cases. And the first one you have distributed load, and the second one you have concentrated load. Okay, in the table you can simply find these two cases. Okay, our case 1, a cantilever beam carrying distributed load is here. Well, this is our case 1. And you can see the equation number 30. This is the elastic curve. Then the case 2 is the simply supported, is the cantilever beam carrying a concentrated load at the free end. It's right here. Right, this is our case 2. And the equation 21 is our elastic curve. Okay, so here in our beam number 1, the elastic curve can be written as Vx equals W x squared over 24 EI by 6L squared minus 4LX plus X squared. Okay, at the free end, what is the value of X? What is the value of X? Of course, X equals L. So we just substitute L into this equation to replace X. So you will get the V at X equals L equals, I left a negative sign here. So you have a negative WL squared over 24 EI by 6L squared minus 4L squared plus L squared. So you will get negative WL to the 4th over 8 EI. Okay, you can see that here is we started from equation 30. Right, this is the equation 30. And after that, we derived this expression, and this is exactly the same as our equation 29. Right? So our beam number 2 here, as we just analyzed, we can start from the equation 21. where the Vx equals negative px squared over 6ei by 3l minus x. Again, at the free end, x equals L. So we just substitute the x in this equation by L. So the Vx equals L equals negative p by L squared over 6ei by 3L minus L. So we get negative PL cubed over 3EI. Okay, again, we actually started from equation 21, as shown here, and we derived equation 20. Okay, here it's totally the same as equation 20. So we just derived the equation 20. So the overall deflection at the free end can be calculated by just simply sum these two together, right? So you get negative WL to the fourth over 8EI minus PL cubed over 3EI. Okay. So here is our final solution.